A very good morning to you all. I'm Akita Patirana and welcome you all to another informative session organized by the Computer Engineering Department at University of Peradeniya. Today's session is about training and transforming deep learning models for optimized inference. To conduct the session, we have Mr. Samurdhi Karnaratne. Samurdhi received his bachelor's degree in computer engineering from University of Peradeniya. He then migrated to USA to enroll in a master's degree program at University of California, Los Angeles. After obtaining his master's degree, he joined NVIDIA, where he now works as a software engineer working in deep learning models. Before moving to the session, I'd like to remind the audience members that if you do have any questions, please feel free to ask them. We have a dedicated Padlet channel reserved just for your questions, and the link will be in the chat. With that being said, let's move on to the session. Mr. Samurdhi, the platform is yours.
Hi everyone, I hope you guys can hear me. Okay, so today's talk is going to be titled "Thinking Ahead: Training and Transforming Deep Learning Models of Optimized Inference." As was introduced, I'm Samurdhi Karnaratne, and I'm a deep learning software engineer at NVIDIA. So in this talk, I'm going to talk about mainly deep learning inference. But more importantly, I want to convince you why you should think ahead about inference when you are engaging in a deep learning project. And I will tell you how you can optimize for inference before training your model and also even after training your model. And I'll stress why you should use an automated inference optimizer library and why it'll make your life easier. And I'll talk a little about my journey as well. So as I said, I want you to kind of grasp why inference is important. I'll try to give you a high-level understanding about the theoretical fundamentals of inference optimization. And at the end, I want you to be convinced that integrating inference optimization to your projects is not hard, and maybe motivate you a little as well. So the required understanding for this, the required level of understanding you need to have is basically like you need to have the fundamentals of machine learning and deep learning. So I'm not going to tell you, for example, what a convolutional layer is. So that's the only thing that you need to know. I won't, assume that you know anything about, optimizing inference. And also, please interrupt me if you have any burning questions. If not, we'll have a Q&A session at the end. Okay, let's get started. So, okay, briefly, I'll tell you who I am. I think this was already covered. So yeah, I like many of you, I think I'm from, Pera Computer Engineering. I actually enrolled as a PhD student. I got my master's. Now I'm actually working at NVIDIA headquarters in Santa Clara, and I'm currently engaged in the TensorRT platform. Okay, so this is what a typical machine learning workflow looks like. So it starts with the data processing stage, right? So you know this step. I think data processing, the modeling steps. You gather the data, you clean it, you transform the data how you want. You kind of design and train a model, and then you do a validation, and then you evaluate your model. These steps, I think, are covered in deep learning courses. But what's kind of left, what's neglected is the deployment part. So you don't think about how your deep learning model is going to perform once you've trained it on new data. How fast is it going to be? How much space is it going to occupy? These types of things are, kind of given a second thought, or even not thought about at all. So that's where I'm going to, focus my talk on. So the deploy to production part is, where our talk is going to be centered. So let's talk about a use case, like, a conversational AI. You all know about these, voice assistants, Siri, Alexa, Cortana, Google Assistant. All these, are based on language models. And these language models are nearing trillions of parameters. They're getting huge. But at the same time, they must service like millions of queries per second, right? So how do you do this? Because data center costs are pretty high, and you need to, give an answer immediately, right? So the latency must be minimal. And, you have to occupy as small a space as possible. I mean, as I said, they have trillions of parameters. So how do you make these models space efficient? And they also need to be power efficient, So how do you kind of make these models conform to these types of requirements? And at an enterprise level, these are critical. They save a lot of money. And this is kind of like another overview of how to think about training versus inference. You design your network, you train it on a particular data set. Then when you're satisfied with it, you kind of deploy, and then you expect it to work on new data, right? And this is the inference part. Okay, so why should you think ahead about inference? As I said, like these deploying models must provide high throughput, right? You must be able to serve a large number of users in a given time. And the response time must be minimal. Like, for example, take like a collision detection system in a car. It has to like react within a certain time frame, otherwise it's going to probably cost a life, right? So these type of response times need to be very small. And they also need to be power efficient. Like think about a deep learning model which is deployed on an embedded device, which has, let's say a very small battery, right? So they need to be very power efficient. And they also need to, be deployment grade. What we mean by that is it needs to be lightweight. Again, if you talk about an embedded device, they usually have very small capacities. So, they must occupy as less of a space as possible. And they also must be, not be dependent on too many, third-party libraries, right? So, most of the DL frameworks that you might be comfortable with, they have a lot of dependencies. So this type of thing is not very attractive during deployment. So can someone tell me, like, let's say you are in optimizing a model for inference. You want it to be high throughput, you optimize it for low response time. What will you be compromising here? Can someone answer that? You must compromise something, right? Can you get all these benefits at no cost?
The time to process something to get
No, of course, the time to process something is what we are minimizing, right? Let's say we bring down the inference latency from, let's say, 1 millisecond per query to like, let's say half a millisecond per query. So you bring down the time to like process something. But at the same time, what will happen to your predictions? Will they be more accurate or less accurate? Like you also need to think about the accuracy, right?
Yeah, it will be less accurate.
Yeah, so probably you might be able to kind of gather from what we are talking about that with all these optimizations we are making, we are probably going to compromise on accuracy. But you might be surprised at how much we can optimize the model of inference while making virtually zero accuracy compromises. So you might lose, let's say, a couple of like decimal percentage points, but you'll get maybe 3 times the space benefits, maybe 10 times the inference latency benefit. So it's really surprising how much you can optimize these models and compromise very little accuracy. So that's the important part. So these 2 graphs are actually data from a project that I did. And you can see that the accuracy drops when you apply something called quantization, which is an optimization to the graph, to your model. The accuracy drops, like decimal places in terms of like, the accuracy percentage. But the latency maybe improves like 2.5 times. So that's like the benefits we are talking about. So you can compromise very little and gain a lot. So that's why you should think ahead about inference. Okay, so how do you actually optimize for inference? So that's the hard part, right? What do you do? So there's 2 ways you can approach this. One is inference-aware training. That means while you are training your model, you can kind of think that, okay, I'm going to be using this in a very latency critical application. So I'm going to make some adjustments to my training workflow such that the training workflow accounts for being able to do inference at a much faster pace than if you didn't consider this before. So this is called inference-aware training, because during the training itself, you kind of tell your training process that kind of please optimize this for inference as well. One of the techniques here is inference-aware quantization, which I'll talk about a little bit later. The other thing is post-training optimization. Here, you kind of train your model and you don't really think about inference at the training stage. You have a packed and ready model, ready to go. And even at this stage, it's possible to do optimization. That's the nice part, right? So if you have an already trained model that probably you have already deployed, you can take that model and optimize it after the fact. And this is a really nice thing. And how do we do it? So one way is, like maybe there are like two broad classes of ways to do this. One is to reduce the effective parameter count. So let's say parameters are like weights, biases, other parameters important for different layers in your network. So weight pruning, weight clustering, these types of methods, which I'll talk about in detail, they reduce the effective parameter count. The other one is reducing the representational precision. So that different data types can be represented in different levels of precision, right? Let's say 32-bit integers, 16-bit integers, 32-bit floats, and all these things. And what you can do is, you can reduce the representational precision of different weights, biases, all these parameters to get benefits in terms of like latency and also space. Okay, let's talk about inference-aware quantization. So inference-aware quantization, as I said, happens at training time. So while you're training your model, this happens simultaneously. So during the forward pass, you kind of simulate low precision behavior. So let's say during the forward pass, you simulate, let's say, 16-bit floating point operations. And during the backward pass, it's, let's say, 32-bit floating point. So the backward pass remains the same, but during the forward pass, you simulate low precision behavior. So the basic technique here is to reduce the quantization error, which the reduced precision induces, right? So if you reduce the precision, the forward pass is not going to be as accurate. So that's going to introduce a quantization error. And you can develop methods which tries to reduce this quantization error. And the benefit here is that inference-aware quantization is better in terms of accuracy compared to post-training quantization. So what that means is if you think ahead about inference and you kind of adjust your workflow to quantize later on, that will result in a lower accuracy drop in your model compared to if you try to quantize your model after training. So that's the benefit, right? So if you think ahead, you'll get a benefit. But it comes at a cost, which is that inference-aware quantization is a more complicated process than post-training quantization. And I won't go into too much detail here, but essentially it's harder to control and harder to tune. So it's a more complicated procedure, but you get the benefit that if you do it properly, you'll get a lower accuracy drop when the quantization is eventually done. So this is the benefit of inference-aware quantization. Now let's go into some post-training optimization techniques. So as I mentioned, this happens after you have a trained model. You try to optimize it for inference. And one thing we can do is, as I mentioned, reduce the effective parameter count, right? Then pruning is a method to do this. So what pruning essentially means is that you increase the sparsity of the parameters of your network. The sparsity, I think you might have covered, some of you might have covered the concept of sparsity, let's say with respect to matrices, right? If a matrix is sparse, then it has, more zeros, right? Or values closer to zero. And you might have, kind of talked about in, math courses that there are certain optimizations you can do with respect to, certain matrix operations when you have sparse matrices, right? Compared to non-sparse matrices, you can do multiple optimizations to make, let's say, multiplication or other operations faster. And this is, similar to that concept. What you try to do is you take the weights of the network and you try to zero out as many of these weights and other parameters as possible. Of course, with minimal effect on the accuracy, right? So how do you do this? And well, before going to that, why is a sparse model better, right? Because of course, if you have more zeros, it would be easier to compress, right? Because you can just forget that those zeroed out weights or biases exist. And during inference, you can kind of skip the zeros, and you can get inference like latency improvements through that, right? Because let's say you multiply by 0, you can kind of ignore that operation, right? So these kind of latency improvements can also be had by doing pruning. So let's say you have a network like this, and and you want to prune it. Like, how do you zero out the weights, right? One simple thing you can do is like magnitude-based pruning. Say you kind of set a threshold for, let's say, the absolute value of a weight, or like, let's say, a bias. Usually biases are not zeroed out because compared to weights, biases don't actually constitute a large fraction of a network's parameters. So let's say you set a weight threshold for the absolute value of a weight of a particular layer, right? And you zero out any weights which don't exceed this threshold. So that's magnitude based. Activation based is you kind of do some like forward passes and you monitor the outputs of certain neurons. And if you kind of if you can monitor that certain neurons produce very low activations most of the time, that means those neurons don't actually contribute much to the predictions given by the network, because they have very low activations. So you can also do this kind of activation-based pruning, where you kind of cut out any neurons which don't produce significant values. You can also take advantage of redundancy. Like if let's say 2 neurons in a particular layer have very similar parameters, then what you can do is, let's say, you can ignore one of these neurons. And there are like methodical ways to do these kind of operations. I'm not going to go into detail about those, but essentially these are the criteria that you utilize. Okay, and another one which actually reduces the effective parameter count is weight clustering, right? This actually reduces the number of unique weights in a model. What that means is, let's say, if you have, let's say, 1,000 number of weights in your model, you can reduce that to, let's say, 100 unique values. And what you essentially do is, let's say, you take a layer and group the weights of that layer into, let's say, n clusters. And how this grouping is done is, it depends on certain methods that you can employ. But essentially, you group these weights into n clusters, and you take the cluster centroid as the representative weight for each of the weights in that cluster, right? So if you have n clusters, you will only have n unique values in that layer, right? N unique weight values. So in this example on the right, you can see, let's say you have a weight matrix, and in this weight matrix, I think you don't have any duplicate values. So essentially you have 16 weights, right? What you can do is group these weights into 4 clusters. So 0, 1, 2, 3, these are the clusters. And for each of these clusters, we can calculate the centroid value. And then what we can do is, okay, we kind of remember what the centroid value is. we remember what the centroid value is, then we can say, okay, this particular weight belongs to a cluster of index 2, so its value is going to be 0.13. So you can just remember the indices, right? So that makes it much better in terms of like model compression, right? So if you apply a particular compression algorithm, you can save a lot of space by doing this because you only have to remember a small amount of unique weights. Okay, so these two methods, try to reduce the effective parameter count. The other one, as we talked earlier, is quantization. This is a different technique where you reduce the precision of the model parameters. So usually you might already know that typically like we train models in FP32, which is 32-bit floating points. But during inference, you don't actually need that much precision in most cases. So you can represent these parameters in, let's say, 16-bit floating points, or let's say 8-bit integers, right? And obviously, this is going to give you, space benefits, right? Why? Let's say a 32-bit floating point is going to occupy half the space that's a 32-bit floating point is going to require. So let's say a model with all weights converted to FP16 will occupy half the space of a model with all weights FP32, right? So that's the space benefit, which is obvious, right? And there's another benefit, which is faster computation. And this benefit actually comes because most modern GPUs can natively operate on reduced precision numbers. So they have reduced precision arithmetic capabilities. For example, let's say NVIDIA GPUs, I think from, let's say, Pascal architecture, which is actually quite old now, can natively operate on FP16. So because of this, actually, again, like you can natively operate on them, and also reduce precision arithmetic takes less time. And thereby you can get a latency benefit as well. So this figure here kind of demonstrates how you would quantize a weight matrix from FP32 to intent. A question here for those in the audience is, why is it harder to use reduced precision during training? You can use it during training, but it's harder. Can you think why it's harder to use reduced precision during training? You need to think about what happens during training, right? There's a forward pass as well as a backward pass, right? And during inference, there's only a forward pass. So why is it easier to use reduced precision during a forward pass as opposed to, let's say, a backward pass? Okay, so yeah, so the reason is, during backpropagation, you need to calculate derivatives, right? And you need to pass them back through the layers. So I hope you guys know what backpropagation is, and that you need to calculate derivatives to do that. And when you are calculating derivatives and doing backpropagation, precision is really important because that's what determines how your network trains. And a small change in precision can have drastic impacts on the trajectory that your training takes. So it can be the difference between your training being very unstable to it being converging really fast. So training is a very sensitive process, and because of that, higher precision arithmetic is really useful. That's why it's easier to use reduced precision during the forward pass as opposed to the backward pass. But modern GPUs like NVIDIA GPUs have Tensor cores, which can do mixed precision arithmetic even during training. So this is like a modern development, but typically it's harder to use reduced precision during training. Okay, so now we talked a little bit about the theoretical background, and ultimately you guys want to use these types of techniques in your projects, in your, let's say, final year projects or your class projects, whatever it is, right? And the good news is that many frameworks and toolkits are currently available for you to do these types of optimizations, and they're pretty easy to use as well. And these types of frameworks, I like to classify myself into two broad categories. This is my classification, the way I see it. So the first type of toolkit or framework is the manual type. So this I call manual is because they require some significant user-led tuning and trial and error. So you need to kind of play around. You need to tune your hyperparameters and see what gives you the benefit. Sometimes it might not give you a benefit. Sometimes it'll make your inference worse. So you need to play around with this. And that's why I call it manual, because you'll have to do a lot of the work yourself. But of course, your favorite libraries, maybe let's say TensorFlow, PyTorch, both these frameworks and others frameworks also have tools to do inference optimization. So TensorFlow has the TensorFlow model optimization toolkit. PyTorch has the prune and quantization modules that you can use for these type of tasks. And I'll tell you, briefly how to, let's say, use one of these tools. The other type of framework is the type of automated frameworks. I call them automated because they do most of the hard work for you. You just need to feed them, let's say, a trained model, and it will figure out what let's say, the best precision to use. Can it use reduced precision? And which reduced precision type should it use? All these types of decisions it can make for you, depending on the target platform in which you intend to run your model. So there's a lot of these as well. The one I work on is called TensorRT. It's developed by NVIDIA. If you're running a model on an NVIDIA GPU, which I think is the case in 99% of the cases, TensorRT is the go-to platform. There are other frameworks on its runtime. It's pretty good. It's maintained by Microsoft. Tencent has CNN, and Intel has OpenVINO. These are less commonly used. So let's talk about how you can use, let's say, TensorFlow model optimization toolkit to do an optimization. Okay, let's see how you can do like weight pruning using the TF model optimization toolkit. So I hope you guys can see this code on the left here. I try to make it as large as possible. So if I apologize if some of these text is too small to read. But essentially, I assume that you've trained, let's say, an MNIST model using whatever procedure you use. So MNIST, for those who don't know, is a very popular data set. It's a handwritten image data set. Like you have like numbers from digits from 0 to 9. And you have to identify from these images of handwritten digits which digit it is, right? But anyway, so let's assume that you have an MNIST model trained. And what you can do is you just import TensorFlow model optimization module. Then here we are doing a magnitude-based pruning. This is one of the pruning methodologies that I talked about, right? So let's say you set a threshold for the magnitude, and you set some batch size. Let's say you are trying to optimize this over 2 epochs of training. You set a validation split. These are all typical procedures, and then you set a pruning schedule. Like let's say you want the final sparsity of your model to approach 80%, meaning that when the pruning is done, 80% of the parameters or the weights of the model need to be 0, right? And that's some constraint that you set. And then you need to recompile your model. So you set your optimizer, your loss function. These are typical procedures. Then you fit your like the model that you intend to prune on a data set that you just created here. This is again similar to how we would train a typical network, right? So what the model optimization tool is going to do is in the background, it's going to run some algorithm to approach this level of sparsity. And this is all you need to do. Once you do this, you'll have a model which is sparse. And if you have the right hardware, or if you use the right compression algorithm, you can get the compression benefit. Okay, so once you do this, for this particular example, the accuracy drops from, let's say, 97.76% to 97.21%. This is a very small drop in accuracy. But let's say the size of the compressed model drops by threefold. So it drops from, let's say, 78,000 bytes to 25,000 bytes. So you get a 3 times smaller model at negligible accuracy loss. Okay, so I'm going to ask a small question. Why do we compare the sizes of the zipped model instead of like the raw model? So zipping means we are applying some sort of compression algorithm before we compare the sizes. Why do we do that? Can someone answer? I think it's a basic question. You don't need to understand your neural networks to answer it. Okay, so it's basically like even if you zero out some of the weights, they're still going to be zero, right? So you still need to represent the zero. If you don't compress it, it's still going to be zero and it needs to be represented. But compression algorithms can take advantage of zeros, right? They can take advantage of sparsity, and during the compression, it helps. So that's why you need to apply a compression algorithm to see the benefit. And this is really important because let's say you want to, you have, let's say, a self-driving car, and you want to, let's say, update the software of the car with a newer model that you've trained. So you need to, transmit that model through the internet, right? So sending, let's say, a 78 gigabyte model versus a 25 gigabyte model, that's the difference, right? So let's say you would rather send the 3 times smaller model over the air to your car than the huge model, right? So you can compress it, you send it over the internet, the car receives it, it uncompresses it, and then it deploys it, right? So that's where the benefit comes in. That's a real life example. Okay, so again, like the thing is, like we talked about different methods, like let's say pruning, clustering, or quantization. Then the nice thing is that they don't need to be exclusive. You don't need to just apply one method and be done with it. You can combine these methods. Let's say you can prune your network. After you prune, you can cluster, then you can quantize. Then let's say you have let's say this is the weight distribution, right? Let's say you have weights, which is roughly, let's say, like a normal distribution, like a Gaussian distribution, right? And what does pruning do? Pruning increases its sparsity, right? So what should happen? Like the number of zero weights should increase, right? So you get a spike at zero. So you have more zero weights. When you cluster, the number of unique weights should decrease. So you should get, let's say, 10 unique weights. So you'll get like 10 peaks, right? So that's what happens when you're doing sparsities. During quantization, what happens is, I mean, the unique number of unique weights and the distribution will stay the same, but of course the representation of precision will decrease, right? So let's say this would be an let's say a floating point distribution. This would be an int distribution, right? That's the difference. But there's a bad news here. The bad news is that even though you can apply these techniques to the same model, it is tricky to make them complement each other. What does that mean? It means that it's hard to get them. Let's say you get a 2 times latency improvement when you prune, and when you cluster, that effect is canceled out. So you don't want these methods to cancel each other out if you apply them one after the other, right? So the problem is that these types of methodologies we use don't actually account for other optimizations being in place. So they can have the effect of canceling each other out. And that's why I said that manually applying these methods is pretty hard, because if you want to get the benefit of applying all these, let's say, 3 methods, it's going to be hard to find the right parameters to set for each of these algorithms such that you get the benefit of all of them. I mean, there are ways to do this. Like, for example, the TensorFlow model optimization toolkit I talked about actually has separate ways to combine some of these methods together, but not all of them. So it's like a limited set of ways you can do it. And that's a disadvantage of using manual methods. And that's why I think you should think about using like an automated inference framework. And that's where something like TensorRT, the Onyx runtime, or any of these other frameworks come into play. So TensorRT is like it's a high-performance deep learning inference framework, and it includes an optimizer and a runtime. So the optimizer will optimize your model, and the runtime is where you run the optimized model. And it delivers like low latency, high throughput, just two of the benefits you can get. And it's designed to run on NVIDIA hardware. This is not a disadvantage because most deep learning work, as I said, 99% of the time it's on NVIDIA hardware, right? So it's great. So it's built on CUDA. So most of the like internal operations happen on CUDA, and it makes optimal use of reduced mixed precision arithmetic capabilities. As I mentioned, Tensor cores in newer GPUs from Ampere and above. So it's intelligent enough to know like if you say, okay, this is my target platform, it can choose different optimization techniques based on the target platform, the model you are using, the batch size, all these parameters it can take into account and do the hard work for you. And you just need to run write a few lines of code. Okay, so what this figure means is you can use any bit, like virtually like a model trained with any of your favorite deep learning frameworks, and you can import it to TensorRT. It can be TensorFlow, it can be PyTorch, it can be Caffe, whatever it is. You can import a trained model in any of these frameworks into TensorRT and get basically the same optimization benefit. So that's the nice thing, right? So you can do the training process on any framework that you currently use, and then just use an importer, and you get the inference benefit. Okay, so what is the workflow that you typically use? Like, let's say you have a trained neural network. This is where you start, right? So the first thing is you have a trained neural network. Then you run it through something called the TensorRT optimizer, which is actually what does the hard work. It kind of understands the target platform, as I said, different parameters like the batch size, and it creates an engine file. So engine file, this is you serialize onto a disk, and you can, let's say, deploy it in any, let's say, embedded device, whatever platform you want, you can deploy it. So if you have the TensorRT runtime on your target device, you can load that engine file onto your device and do the inference. For example, if you have a self-driving car, you have the TensorRT runtime on it, you send it a TensorRT engine, and it can just do the inference. So it's a very simple procedure, and it actually is as simple as that, so you'll realize it. Okay, so how does actually TensorRT work? How does it make these types of optimizations? How can it do better than, let's say, you using a manual framework and trying to optimize your network? So it basically does like 5 things to like optimize your model. One thing is precision calibration. This is the quantization I talked about. It's also it's called precision calibration because sometimes you also need to do calibration in terms of, like, let's say, integers, but let's say it basically determines which precision your network could run at to get the optimal performance. It also does something called layer fusion, which I'll talk about later. And it also does kernel auto-tuning, which I'll also talk about later. And it also has dynamic tensor memory. So it will kind of dynamically allocate and deallocate memory in your GPU such that the memory footprint is as low as possible. It will also do multi-stream execution. This is important for throughput. Let's say it can actually process multiple streams of input, let's say multiple requests at the same time on the same model. So this is the multi-stream execution benefit. And now I'll talk about these three techniques at the top: precision layer fusion, kernel auto tuning. These are the most important optimizations TensorRT does. Okay, so the optimization one is layer and tensor fusion. So let's say you have, let's say, deep learning model, right? This is not a complete model. Let's say you have to read this model from the bottom. So you have a concatenation layer, then you have an input, then you have a bunch of like ReLU layers, bias layers, a bunch of different convolutions. You have 1x1 convolutions, 2x3 convolutions. You have a bunch of these layers. And then you go to the next part of the network, right? So what I mean by computational graph is that let's say a neural network can be represented as a computational graph where each node of the graph is a different operation. I think you guys might have done, like, let's say, graph theory or something like that. So you know what a node is, so let's say a computational graph is just basically a graph where the nodes are different operations, and the weights are directed such that the second operation is at the edge, the end of the edge, and the operation we should precede it as at the start of the edge. So this is a directed graph with nodes representing operations. Anyway, so can you see an optimization we can make, or can you make an observation about this graph? What can you see here? There's a lot of redundancy. Can someone point it out? I would be really happy if someone can say, okay, there's this type of pattern in this graph. Can you see some groups here, like, let's say, groups of operations which are close to each other? Okay, let's say you have a convolution, a bias, and a ReLU, right? So can you see multiple such blocks of operations here?
Yes.
Yeah. So you can see that, let's say there's actually, like, if you count, there's like 6 blocks of convolution followed by a bias, followed by a ReLU activation, right? So you can think about, okay, why this is, if you think about this as a single operation, it's like a convolution followed by a bias followed by a ReLU. Can we make this a single operation and maybe try to fuse these layers, these blocks of 3 layers into one? And that's the idea we basically have with layer fusion. You can see that we can see multiple blocks of convolutions followed by biases by ReLU, right? But okay, so what we want to do is, instead of doing 3 operations, let's say as I said, each of these nodes or each of these like rectangles are nodes of a graph, and each node represents a separate computation, right? So here you would do 3 operations. Here you would do 3 operations. Here you would do 3 operations. And each of these blocks would constitute 3 operations, which is expensive, right? You would rather do 1 operation instead of these 3. So that's the idea of fusion. So what we can do is, let's say this block, we can say it's a 1x1 CBR operation. That means it's a 1x1 convolution followed by a bias and a ReLU. You can take the 3x3 convolution layers and say, okay, these are 3x3 CBR operations, right? You can say these are 5x5 CBR operations, right? So you can see that we kind of fused these operations together to form one operation. And that's vertical fusion because we fuse the layers vertically, right? That's called vertical fusion. And why does this vertical fusion help? Okay, we fused it. We said, okay, it's just 1 computation instead of 3 now for each of these nodes. But why does it help? Okay, so if you think about this in terms of how this graph is going to be computed, as I mentioned, like each of these operations are going to be executed on the GPU, right? So a GPU operation happens when you do something called a kernel launch. I don't know whether you guys did parallel programming or if you talked about CUDA, but anyway, each operation is actually going to be offloaded to a separate kernel launch. So each operation you say, okay, you tell the GPU, please do this operation on the GPU and give me the outputs. And that's what basically a kernel launch or kernel operation means. So let's say if you do it the traditional way, you would do a convolution separately, a bias separately, a ReLU separately. And for each of these, there's something called the launch overhead. So each time you launch a kernel, it takes some overhead because of certain processing delays and such. Because of this, there will be some latency at it. There's also the data transfer, or the read-write overhead, right? So let's say you do a kernel launch, you get the output, you have to write it back to the GPU memory, you have to read it from the GPU memory, you have to write it back, you have to read it. So this read-write latency also adds up. So that's where we get the savings, right? So if you just do one operation, you'll have just one kernel launch, one read, and one write, right? So that's the benefit. You'll get the benefit of doing just one read, one write, and one kernel launch. If you haven't done CUDA, this will be much clearer when you talk about what kernels are, but I'll talk about what kernels are later on as well. But anyway, so you can also do something called horizontal fusion. What this means is that you can see that, for example, in this vertically fused graph, which you just created, some of these CBR blocks take the same input and they have the same size, right? For example, these 1x1 CBR blocks, they take the same input. You can see the input going from the same input block, and they have the same size of convolution, right? And if these convolutions have the same parameters as well, for example, the stride, these type of parameters are also the same, then why do you repeat the same operation for the same input 3 times, right? You can just do one time and copy the output to wherever it needs to go. This is called horizontal fusion. So you can see on the right-hand side, we have taken these 1x1 CBR blocks, these 3 1x1 CBR blocks, and made it one operation. So instead of doing 3 operations, we feed the input to the CBR block, we take it and we copy it to wherever it needs to go. So now you have just one 1x1 CBR block. So now you've reduced the number of computations from how many? Like let's say you have you had 6 here. So 6 by 3 is 18. You had 18 computations. It came down to I think it's here 6, and now here it's 1, 2, 3, 4. So it came down to 4. So this is the advantage you get, right? You reduce the number of operations. This is called horizontal fusion because you kind of merge the layers horizontally. Yeah, so I just explained what happens. You just take layers which have the same input and the same parameters and just fuse them. Okay, so if you didn't understand what a kernel is, basically a kernel is something that you do on the GPU. It's like a function which runs on the GPU. So in your CPU code, you can say, okay, I have a kernel function called, let's say, my kernel. I want to run some operation on the GPU. So you can say my kernel, and you specify some parameters, and you say, compute this function on the GPU for the input X, right? That's called a kernel launch, because you're basically launching a kernel on the GPU from your CPU code. And a kernel is basically a function which runs on the GPU. So the second optimization is kernel auto-tuning. This means that for the same operation, for example, a convolution, we can have multiple possible kernels, meaning that there could be multiple ways of doing the same operation. Why? Because even for, let's say, a convolution, there are different algorithms which exist. For example, there are like optimized algorithms for convolutions, like let's say Vinograd convolutions. There's something called a variant of convolutions called depth-wise separable convolutions, which are much faster. And for these, different type of algorithm, you could have a different kernel, right? There could also be different kernels based on the GPU. Let's say you have an RTX 3090 and another person has an RTX A100, right? Based on the target GPU, each GPU has different number of tensor cores. They support different, different operations. So based on the GPU, also you could have different kernels. So what TensorRT could do is, depending on which platform you intend to run it, depending on your model, it can decide which kernel is the best suited one, and can pick this from a library of kernels and just automatically input it. So you don't see it happening, but it will do the pick the best one. So that's called kernel auto-tune. The other one is reduced precision, which we just talked about, right? So usually we train models in FP32. So we import that model and we can run it in FP16. This has been around for a long time. As I said, this has been around since Pascal. You can run it in int8. With int8, you only have, let's say, 256 different values, right? 2 to the power 8. So you need to kind of calibrate your, let's say, floating point values to figure out the range of values. So you need to do a calibration. So there's an extra step involved here. But int8 saves a lot of space and time because it's just 256 values, right? There's another one called TF32, which was introduced in the Ampere architecture, which is the, let's say RTX 3090. These are Ampere GPUs, right? Ampere GPUs has a data format called TF32. And this has, the same precision level as, let's say, a 16-bit floating point, but it also has the same range as a 32-bit floating point. So if you see this figure on the right, it uses the same 10 bits as an FP16 to represent the precision. And for the range, it uses the same 8 bits as an FP32. So you get higher range at a lower precision. So you kind of make a compromise. The nice thing is this only occupies with the sign bit, only 19 bits, right? So instead of 32 bits, you kind of boil it down to 19 bits and you get the same range. So this is a really nice compromise to make, for especially like deep learning applications. And this is available in the Tensor cores of newer GPUs like Ampere, now Hopper. These GPUs have this type of capability. So as I mentioned, reduced precision arithmetic takes less time. It has a small footprint, and there's less bandwidth pressure, right? So this is the important part. How do you get started with TensorRT? And it's really easy. So it's free to use. So a lot of the, except the core code of the optimizer and the runtime, the demos, the plugins, the parser that we use, samples are all open source. So you can view them on GitHub. It runs on Linux and Windows, 32-bit, 64-bit platforms. It supports almost any operation you can think of that's widely used in neural networks. And even if you have a custom layer, you can implement it using something called the plugin API. And it also has Python and C++ API, so you can code in either language. So that's nice as well. So to get started, you just need to go to the TensorRT website on nvidia.com. You can install it bare metal on your, let's say, laptop or your workstation. But the best way to use it is to use container orchestration. Let's say you have Docker containers which you can launch, and all the dependencies are handled. So you just launch the Docker container, then you can just run your script, and you can do the inference really fast. So all these containers are available at NVIDIA and GC, and it's probably the easiest for most use cases, instead of just trying to install it bare metal on your workstation. So importing a trained model to TensorRT is really easy, because almost any deep learning framework that you can think of, let's say TensorFlow, PyTorch, Caffe, all of these have importers, actually exporters, to a format called Onyx. So Onyx is like an open source interchange format for different deep learning model formats. So all these libraries have exporters. For example, in TensorFlow, this is all you need to do to export a TensorFlow model to an Onyx model. So you have something called TF to Onyx. This on line 5, you can see that there's a module library called TF to Onyx. So after you train your model, you just need to run like a command saying, okay, I need to convert this to Onyx model, and you can just get an Onyx model just like that. So it's really easy. And once you have an Onyx model, you can import it to TensorRT. So after you have that, you can use the standard Python API, which TensorRT provides, which allows for a lot of customizations. It's really flexible. You can do a lot of fine tuning. But for most use cases, I think at the undergrad level, you can use something called polygraphy, which is a tool which is written to help run simple use cases. So it makes a lot of these things really easy. So I'm going to give you an example using polygraphy. So again, this is all it takes to run an inference using polygraphy and using TensorRT. It's like maybe 20 lines of code, right? So it's really easy. So you just import the relevant functions from the polygraphy backend. So let's say you saved an Onyx file, right? So you can see that there's something called identity.onyx. So this is just a sample model which performs an identity operation. It doesn't do anything to the input. It just passes the input to the output just for the demonstration purpose. So you can see I want to build a TensorRT engine from this Onyx file. So that could be any model that you train. And what you can do is you can just say there's something called the TRT runner. So with TRT runner build engine, so the build engine you can input here, you can say, okay, this is my input data. So it could be a NumPy array. So you get the NumPy array from your data set, wherever it is. Then you say runner.infer, and you provide it a dictionary of input values. So in this case, you just have one input. So that will be your input data. And when you call infer, it will give you the output. It's as simple as that. And the nice thing is this particular operation will run much, much faster if you use TensorRT instead of just running it on, it's a TensorFlow model, through your TensorFlow model. And all it takes is 20 lines. So that's why I say it's as easy as that. It's free. So just integrate it to your projects, and you'll see the benefit, right? Okay, so I think we are kind of coming towards the end of the talk. So I was also told to kind of go through my journey and how I got to where I am. So I started again, like most of you, at computer engineering at University of Peradeniya. So mostly I focused on competitive programming, apart from the academics. Actually had zero coding experience before I came here. So the Hackers Club, I think, which still exists, they ran a coding competition at night. I joined that. I kind of realized I had some knack for programming, and that's where I began. So I spent a lot of time on coding competitions online and in real life as well. So my team won SS Coders, IEEE Extreme, the Sri Lankan leaderboard. So I got my experience there. So for my internship during my undergrad, I went to Nokia Bell Labs. I was a research intern there. This is in Belgium. I worked on machine learning applications in like mesh Wi-Fi networks. Mesh Wi-Fi networks are like you have multiple access points. So how do you run different algorithms using reinforcement learning? These type of things I did at Nokia Bell Labs. So after my graduation, I enrolled as a PhD student at UCLA. That's University of California, Los Angeles. And I got my master's degree just last year. There, I spent a lot of time on deep learning applications in wireless networks, like Wi-Fi, 5G networks. So my research was mostly on like open set classification, which is as opposed to, let's say, closed set classification, which I usually do with neural networks. I also spent a lot of time on adversarial attacks, which you guys might know, and also generative models, like let's say GANs. These are the type of research I did there. During my time at UCLA, I also interned at Qualcomm, headquarters in San Diego. I did research on Wi-Fi 7, which is the next generation Wi-Fi, probably going to be released in 2023. Then after that, I went to NVIDIA. I'm currently working at Santa Clara headquarters, and I'm the lead developer for the TensorRT plugins right now. So I guess what helped me is mostly just you just need to have math fundamentals, I guess. And algorithms and data structures are the key. And what I want to stress is that the curriculum that you cover in your undergrad is not going to be enough for most cases. You need to cover more than that and more complicated type of algorithms. And I think if you do your self-study, I think that's really beneficial. And just focus on your undergrad research. It's really important. Don't take your final year projects for granted. Make a publication out of it, and keep in mind that the internship you have is really important, and it's probably more important than you think, because you just get 1 6-month internship versus 2 for other people, right? So you need to spend it wisely. You need to make it count. And the connections I made at my internship actually really helped me, to kind of explore my aspirations. So make it count. I'll also talk about what I do on a daily basis. So the TensorRT team, I usually spend most of my time designing and developing new features for, let's say, newer deep learning models which are being introduced every day. So we have to write optimized kernels for those using CUDA. So I write a lot of C++ code and CUDA code, and also a little bit of Python code. And I spend a lot of time reviewing other people's code. I write tests. I get to work with customers. But what I like is that I get to work at the intersection of deep learning and also classical algorithms. So I get to use most of these classical algorithms, let's say depth first search or breadth first search or knapsack algorithm, whatever it is, right? I get to use these algorithms as well as kind of be at the I have a front row seat to the deep learning developments, because we have to be updated on those. And I also get to work with some of the best programmers and engineers in the world, which is really eye-opening and a really transformative experience. So just talking about NVIDIA, I've enjoyed my time here. It's a really nice organization. You can talk to anyone. You can ask questions from anyone. And it's also a really nice place to be in. It's at the heart of Silicon Valley. So you have just a nice culture. So if you like hardware-centered development, if you like deep learning, there's also a lot of research going on in NVIDIA. It's, I think, the place to be. So yeah, I think that concludes my talk. And yeah, thank you so much for listening. And if you have any questions, suggestions, complaints, I'm pleased to hear them.
Thank you very much for that interesting and engaging session. And now it's time for the Q&A. So if you have any questions, you can either unmute yourself and ask, or put them in the chat. In the meantime, there's a small poll that we prepared for the audience members. So I'd like to ask our audience members to go ahead and fill that poll. We have one question in the Padlet channel. The question is, can we optimize inference process by having better input format? In brackets, small.
Sorry, I didn't hear the last part.
In brackets, smaller files. The question is, can we optimize inference process by having better input format? In brackets, smaller files.
Smaller files?
Yes.
I'm not sure what you mean by smaller files, but I don't know whether what you are referring to is the way you represent a tensor. There are different ways you can represent tensors. They're called tensor formats. So let's say you can have, let's say, NCHW, where you have the batch dimension first, the channel dimension first, let's say height and width next. You can also have, let's say, NHWC, where you have the channel format next, the channel and the last dimension. I'm not sure whether you're talking about that. If you're talking about that, yes, if you have an input which uses one format versus the other, then you can get benefits, because TensorRT makes certain optimizations, and some of these optimizations are only available for certain tensor formats and not for the others. If you're talking about data types by format, I think you should be using higher precision like numbers when you're doing training. You shouldn't try to optimize by, let's say, doing your training on FP16, because usually that could go wrong pretty fast. So use the highest precision you have available when you're doing training. I mean, if it doesn't constrain whatever resources you have, then during the inference you can optimize it for reduced precision. That's what I would say. So yeah, you don't try to save on the let's say model size by reducing the precision during training. You can do it afterwards. I don't know whether the question was answered or not. Sorry.
So if the person has any doubts, they can clear the doubts, and I don't think we have any other questions. So once again, I'd like to thank our resource person, Mr. Samudhi Karunaratne, for taking the time. And thank you for the audience members for joining. And we'll meet you soon with another session.
Thank you.